welcome back. This is Unit 5.2. These are the gas laws, and the reading that you need to do is page 474 through 499. And in your study guide, it's 199 to 213. All right, so first off, we need to look at the different laws that are used to describe the behavior of gases. And the first law that you need to write down is Boyles Law. And Boyles Law deals with pressure and volume of a gas, just pressure and volume, just those two variables. All right, so if we think about the different variables that affect a gas, there's pressure, volume, and temperature, and moles. So those four. So if we're just using Boyles Law and it's just dealing with pressure and volume, then what two variables are being held constant? Okay, so that would be the temperature and the number of moles. So those aren't changing. So the temperature and the number of moles are held constant. And then the pressure and volume are being changed. And if you look at the behavior of a gas, we think about the kinetic molecular theory. If we put a gas under pressure, so if we pressurize a gas, then the volume is going to decrease. So think about an air compressor. So an air compressor will take air out of the atmosphere, atmospheric air, and compress it into a tank so that you can put air in like your tires of your car or the tires of your bicycle, things like that. So it takes the air from the atmosphere and compresses it into a tank. Okay, so when you put it under pressure, more pressure, then the volume is going to go down. All right, so if we look at this, if pressure goes up, volume is going to go down. Is that a direct or an inverse relationship? Okay, so the definition of that is this: if it's a direct relationship, then they would both do the same thing. For example, if we increase the pressure and the volume also increased, that would be a direct relationship. But since it doesn't, since pressure goes up and volume goes down, that's going to be an inverse relationship on that. All right, and so the formula for Boyles Law is P1V1 is equal to P2V2. Now remember, these ones and twos mean before and after, or the ones signify a initial or a starting situation, and the twos are a final or after some change has been made type of situation. Okay, so the P1V1 is equal to P2V2. Okay. Now, Charles' law, another scientist working with gases, just worked with the volume and temperature. And so volume and temperature are changing. Which variables are being held constant? Okay, so that would be the pressure and the moles. Okay, so those aren't changing in Charles' law. It's just the volume and temperature. All right, and so if we think about the kinetic molecular theory, anytime we increase the temperature, what does the volume of a gas do? Well, if we increase the temperature, that means that the molecules or the atoms are moving at a quicker pace. And if they're moving quicker, then they're hitting the inside of the container more often and harder. Now, if the container is a flexible container, like a balloon, where a balloon is able to expand and contract, then the balloon, if the molecules or atoms on the inside of the balloon are hitting harder and more often, then what's that going to do to the balloon? Okay, of course, it's going to make the balloon get bigger, so the volume is going to get bigger. So if we see here, they're doing the same thing, that's considered a direct relationship. All right, the next one we're going to talk about is Gay-Lussac's law. And Gay-Lussac worked with pressure and temperature. And what's being held constant? Okay, so that's going to be volume and moles. All right, so this is going to be like in a rigid container, like a paint can, where the walls don't expand or contract significantly. So if you have pressurized gas in a rigid container, like an air compressor tank, okay, if we increase the temperature, what is that going to do to the pressure? Well, if the tank walls can't move, it's a very rigid container, then what's going to happen is, remember the definition for pressure is how often and how frequent the atoms or molecules hit the inside of the container. So if you're heating this up and the particles are moving quicker, they're going to hit the inside of the container more often and with more force. So that's going to make the pressure go up. All right, so again, this is a direct relationship. All right, and so the final law we're going to talk about in section 3, 5.3, and that's Avogadro's law. And Avogadro's law is the number of particles per volume. So we'll talk about that when we get to section 5.3. So for this, we're only going to talk about these 3 laws. All right, so if we take all of these 3 laws and we put them together, so I think I neglected to tell you that this is a formula for Charles' law. P1 over T1 is equal to V2 over T2. And the formula for Gay-Lussac's law is P1 over T1 is equal to P2 over T2. If we take all 3 of these laws, Boyles, Charles, and Gay-Lussac's, and we combine them together, then we're going to get what we call the combined gas laws. Okay, and this is the formula that we're going to be working with. Now, you'll need to know for test purposes that Boyle's law is pressure and volume, Charles' law is volume and temperature, and Gay-Lussac's law is pressure and temperature. Okay, and then the combined gas law is going to be given to you on your reference materials. So that's P1V1 over T1 is equal to P2V2 over T2. Now, if we're working out a problem and it's just a volume and temperature problem, and it says that there's no pressure, or it doesn't give you the pressure, or it says that the pressure stays the same, then what we do is we just mark off that variable in the combined gas law, and we just use the volume and the temperature. And if we do that, what do you see here? V1 over T1 is equal to V2 over T2. All right, that's going to be Charles' law. And same thing, if we take, and get a bigger brush here, and say the problem doesn't give us any volumes, or it says that the volume is being held constant, we can cross out the volume. So all we have is P over T. You can see that that is Gay-Lussac's law, right? So all 3 of these laws are combined into one formula. All right, so make sure you pause the video and you write all this down. All right, so let's do some examples. All right, so here we have a question that says a sample of gas at 1.4 atmospheres increases in volume from 250 milliliters to 400 milliliters at a constant temperature of 30 degrees Celsius. What is the final pressure of the sample? Now, on these problems, since we have these 3 variables in this section, and in the next section, 5.3, we're going to be having 5 variables, it is vitally important that you have some kind of organizational method to solve these problems. And I've given that to you in class that we've been using all year long, and that's the GLUES method, G-L-U-E-S. So make sure that you start using that, okay? So what that means is we're going to identify all of our givens. So we're going to circle these. So 1.4 atmospheres, 250 milliliters, 400 milliliters, okay, constant temperature of 30 degrees. That's a given, but I'll show you what to do with that. And then list those out. So we're going to have 1.4 atmospheres, okay, and that's going to be equal to a pressure. Okay, so that's the variable P. 250 milliliters. Okay, and that's going to be equal to a volume. 400 milliliters. Okay, and that's also a volume. And a temperature of 30 degrees Celsius. Okay. All right, so we've listed out with the variable that represents that data. So the next step is to underline your unknown. What is the final pressure? So we're looking for a pressure. So question mark is the pressure. All right, so now let's write out our equation. So P1 V1 over T1 is equal to P2 V2 over T2. All right, so our problem says that we have a constant temperature. So what that means is that the temperature is the same before, which is T1, as it is after. So T2 is the same as T1. So if it stays the same, we can eliminate that variable in your problem. So really, we have P1 V1 is equal to P2 V2. All right, so whose law is that? Well, let's look back. That is going to be Boyles Law right here. Okay. All right, so we're just working with pressure and volume. All right, so since we have P1 V1 and P2 V2, since we have ones and twos, we need to decide what's the initial or starting values and then what is the ending values. So 1.4 atmospheres, is that a starting or an ending? Well, here this says what is the final pressure. So that's obviously the ending that we're looking for. So that's P2. So that must mean that the 1.4 atmospheres is the P1, the starting pressure. Okay, and then 250 milliliters. So it tells you in the problem that it increases in volume from 250 milliliters to 400 milliliters. So that must mean the 250 milliliters is the V1 and the 400 milliliters is the V2. All right, so we have all of our variables here labeled as P1s, V1s, V2, and P2. So now we can look back at our problem. We're going to be solving for P2. So what I like to do is, just for me, I like to put a box around what I'm solving because I have to move the other variable. So what I'm going to do is clean this up a little bit so that we don't have that temperature there since we don't need it. It's a constant. Okay. So there's our formula. We need to hold that P2 in place because that's what we're looking for. So we need to get rid of the V2. So in algebra, if we're trying to get rid of something that's multiplied by another thing, then we do the inverse. So I'm going to divide both sides by V2. Now, if we do something to one side, we have to do it to the other. So when we do that, V2 is going to cancel here. So that leaves us, our formula is P2 is equal to P1 V1 over V2. So that's what you want to do. You want to rearrange your formula so that you can get what you're solving for on the equal sign by itself. Now, once you do that, now we can plug in values for these variables. All right, so P2 is equal to, what are we going to plug in for P1? Well, we need to plug in the value right here. So that's going to be 1.4 atmospheres. Now make sure that you're in the standard units for gas problems. And the reason I say that is because V1 is 250 milliliters, and that's milliliters. We can't use milliliters in gases. It has to be in standard units. So the standard units for volume is liters. So we're going to have to convert that to liters. All right, so the quick way to convert that is just to move the decimal places 3 places to the left or divide this by 1,000. Okay, and we did these conversions last week. So if we do that, that's going to be 0.250 liters. Okay, over in V2, make sure you use your units. You must. I know it's a hassle to write units down. I didn't like to do it either when I started, but it's a must. If you don't write units down on every problem, you get lost. All right, V2 is 400 milliliters, so that's a 0.400 liters when we change it to standard units. So that's our problem. Now, the reason I say that it's so important to write down your units, because you see you have liters on top here and you have liters on bottom. And remember, what's on top can cancel what's on bottom. So those liters can cancel out. So the only unit you have left for this problem is in atmospheres. So we're going to get, when we do this math, we're going to get our answer in atmospheres for pressure. So let me grab my calculator here. All right, so plug this in. All right, so we have 1.4 times 0.250 equals, and then divided by 0.400, you're going to get 0.875 for the answer. All right, so now we need to look at significant digits. We're going to look at all of our given data for significant digits. All right, so we didn't use this 30 degrees in our problem, so we can cancel that out. So 1.4, 250, and 400 point, that little decimal there is significant as far as knowing how many sig figs we have. All right, so it looks like 2 significant digits is what we're looking for our answer. So we have 0.875. Here's my first, here's my second. So we're going to look at the third one to see if we round. And a 5 does round, so we have 0.88 atmospheres is our final answer on that. Okay, so that's how you do these problems. So we are going to do another example. Make sure you have that written down in your notes. Now this one I'm going to go a little bit faster since I've already showed you how to do one, so we can go a little bit faster on this one. Make this video shorter. A sample of neon gas in a rigid 1 liter container, okay, at 15 degrees Celsius has a pressure of 600 point torr. What is the final pressure if the sample is heated to 100 degrees Celsius? All right, so we have 1.0 liters. That's going to be a volume. 15 degrees Celsius. It's going to be a temperature. Pressure, 600 torr. It's going to be a P. Final pressure, so we don't know. That's what we're looking for. So we're looking for final pressure. That's P2, so that must mean that's P1. I can go ahead and label that. If the sample is heated to 100 degrees Celsius. Okay, so that's a temperature. All right, so we have P1 V1 over T1 is equal to P2 V2 over T2. And V1 is, oh, well, it says 1 liter container. It's a rigid container. That means that the size of the container cannot change. It's like a paint can. So really, this volume is going to stay the same. All right, so if the volume stays the same, we have P1 over T1 is equal to P2 over T2. So whose law is that? That's Gay-Lussac's law, pressure and temperature. All right, all right, temperatures. All right, so it starts off at 15 degrees Celsius and it's heated to 100 degrees Celsius. So that's going to be T2, the 100 degrees. So the 15 is going to be T1. All right, so we can either rearrange our formula or we can convert our temperatures to Kelvin. So I'm going to go ahead and convert our temperatures to Kelvin first because we cannot use Celsius in these problems. It has to be in standard, which is Kelvin. So 15 plus 273. Now remember, if you're going from Celsius to Kelvin, you add. That's going to be 288. Oops, 288. All right, and then 373 Kelvin for that temperature. All right, now we can go ahead and rearrange. Well, I'm going to erase this so it doesn't get in my way and confuse me. And we're solving for final pressure, so that's going to be P2. So I'm going to put a box around that to know that I'm not going to move that. That's locked into place. So to rearrange this, I've got to move this one up here. So our formula is going to be P1 T2 over T1 is equal to P2. Now I can start plugging stuff in. P1, 600 torr, times T2 is going to be 373 Kelvin over T1, 288 Kelvin. Okay, Kelvins cancel, so my answer is going to be in torr for my final pressure. Okay, so plug in my numbers, 600 times 373 divided by 288. That's going to give me improper fractions, so all right, so that's going to be right here, 777.083. Pardon me. So that's the raw answer on the calculator. Now we need to figure out how many sig figs. Well, we didn't use volume in our calculations, so we're not going to worry about that. So 15 degrees is 2. 600 torr. All right, so if you look at the original, there's a decimal there after the 600. So that means that that's 3 sig figs. And then the 100 degrees, there's a decimal there. So that means that's 3 sig figs. So the lowest is 2 significant digits. All right, so 2 significant digits. Here's 1, 2. So we're going to look at this third one to see if it rounds. And the 7 does round this, so this is going to be 78. We can't drop that off because it's before the decimal, so we have to have a placeholder 0. Please do not forget about those placeholder zeros when they're on the left side of the decimal. So the answer to this problem is 780 torr. Okay. And let's do this. All right. So here's our combination gas law. P1 V1 over T1 is equal to P2 V2 over T2. And everything is fine. And you use it just like I have been working these two problems, unless we're solving for temperature, either T1 or T2. So if you're solving for temperature, let's rearrange this. Let's say that we're solving for T2. So I'm going to put a box around that so that I can hold that in place. And when I rearrange this, I'm going to get P1 V1. These are going to move down to here over T1 P2 V2. Okay, so that's going to be equal to, now when we cross these out, they just don't disappear. They change to 1. So that's going to be equal to 1 over T2. Okay, and so here's your problem. We don't want 1 over T2. So when we solve this, just let's say we solved it and we came out with 298 Kelvin as our T2 temperature. Well, if we use this formula, that's really 1 over 298. And that's not what we want. So what you have to do is you have to flip this one so you can have it not a fraction. And if we do that, we also have to flip this side. So the formula is really T2 is equal to T1 P2 V2 over P1 V1. So that's the formula for solving. We don't want the inverse of T2. Okay, we want T2. So we have to flip both sides in order to do that. So this is your true formula. So be careful when you're solving for temperatures that you do that. So let's look at a problem where we're solving for temperatures. So we have a sample of hydrogen gas at 1.5 atmospheres and has a pressure, had its pressure decreased to 0.5 atmospheres, producing a new volume of 750 milliliters. What's the sample's original volume if the temperature remains the same? All right, so the temperature is constant here. We don't have to worry about the temperature. But we do have 1.50 atmospheres. Let's go ahead and list these out. That's a pressure. Okay, and we had its pressure decreased to a 0.50 atmosphere. So that's the change. So that's the P2. So it started off at 150. I'm sorry, 1.50, and it was decreased to that. All right, and so it produced a new volume of 750 milliliters, new volume, so that's going to be a V2. So what we're looking for here is the original volume, original V1. All right, so this is Boyles Law, pressure and volume. So P1 V1 is equal to P2 V2. So we don't even have a temperature in this. I think I put the wrong question there. Oh well, let's go ahead and work it since we started, and then I'll do one where we have a temperature. All right, so we're looking for V1. I'm going to put a box around this. So P1 is going to come down here. Okay, so V1 is equal to this. All right, so this has to be 0.750 milliliters. I'm sorry, liters. There you go. All right, so let's plug in. So P2 is 0.50 atmospheres times V2, which is 0.750 liters, over P1, 1.50 atmospheres. Okay, atmospheres cancel, so we're going to get an answer in liters. So let's go ahead and plug in our data. So 0.5 times 0.75 divided by 1.5 equals 0.25. Okay, now how many sig figs? Well, we got 3 here, 2 here, because the 0 leading doesn't count, and the 0 after does because there's a decimal, and 2 here. So 2 significant digits, so 0.25 is going to be our answer. Okay, so let's look for that one that's got the temperature. Temperature remains constant. What pressure? Helium occupies what volume will this occupy? What is the new volume? What was the original temperature? All right, so this is the one that I wanted. So we have a sample of nitrogen that was transferred to a 100 milliliter container at 100 kilopascals and 75 degrees Celsius. What is the original temperature if the gas if it occupied 125 milliliters and a pressure of 125 kilopascals? All right, so 100 milliliters, 100 kilopascals, 75 degrees Celsius. Okay, so this is the volume, this is the pressure, this is the temperature. What was the original temperature? So that's going to be T1, so that must mean that's T2, of the gas if it occupied 125 milliliters. Okay, that's a volume, and exerted a pressure of 125 kilopascals. That's a pressure. A sample of nitrogen was transferred to a 100 milliliter container at 100 kilopascals and 75 degrees Celsius. What was the original temperature of the gas if it occupied 125 milliliters? All right, so that's a V1. So V2, because it was transferred to a 100 milliliter container. So that's a smaller container. So that's the after. And so that would make the 125 also a P1. Okay, so that would make that a P2. All right, so P1 V1 over T1 equal P2 V2 over T2. All right, so we have all 3 variables here. What was the original temperature? So that's T1. Okay, so we need to move P1 and V1 down here to get rid of it. That makes that 1 over T1. So here's where we have to invert. So it's T1 is equal to T2 P1 V1 over P2 V2. That's our formula. All right, so this is going to be equal to 0.1 liter. Kilopascal is good. 75, so take 75 plus 273, convert it over to standard units, 348 Kelvin. Okay, volume 0.125 liters, and kPa is good on the pressure. All right, so let's plug in T2, 348 Kelvin times P1. It's going to be 125 kPa times V1. It's going to be 0.125 liters over P2. That's going to be your 100 kPa times V2. It's going to be your 0.1 liter. All right, liters cancels, kPa cancels. So we're going to get our answer in Kelvin, which is what we want because we want to know the original temperature. All right, so plug and chug. 348 times 125 times 0.125 over 100 times 0.1. Okay, we're going to get 543.75 sig figs. All right, so we have one sig fig here. We don't have to go any further because one sig fig is the lowest we can have. So 543 rounded to one significant digit. Well, here's the first one, so we're going to look at the 4. Does the 4 round the 5? Nope. We're going to keep the 5. These two are on the left side of the decimal, so they become placeholder zeros. So there's your answer, 500K. All right, so every problem is basically worked the same way. You just got to find out what's the before and the after values. You have to make sure they're in standard units. You have to know how to rearrange that formula. And then it's simply just plugging in the numbers and using your calculator to get an answer. Then looking at the significant digits and reporting the correct number of significant digits. All right, so let's slap that like button right across the face. Give me a thumbs up and subscribe so that you can know when I put up new videos, because sometimes they go up on YouTube a day earlier than I put them in Canvas. See you in class.